Picture this. You've just made a massive investment. You've purchased a bare horizontal machining center and an HMC.
Right, a serious piece of hardware.
Exactly. We are talking about a heavy-duty, multi-ton industrial machine designed to cut solid blocks of steel and titanium, and with absolute, unforgiving precision.
Yeah, you expect perfection out of the box.
You really do.
Yeah,
You get this behemoth installed, you power it up for its initial test cuts, and as the spindle spins up to speed, your heart just sinks.
Oh, man. The worst feeling.
You lean in, and you see it. The spinning cutting tool is, well, it's wobbling. Not a lot, maybe just a hair, but in this world, that tiny microscopic wobble is enough to completely ruin the parts you were trying to make.
It really is the ultimate sinking feeling for any machinist. I mean, you expect this massive block of cast iron to just be perfect right out of the gate.
Right.
But that wobble, what the industry actually calls spindle runout, it's a stark reminder that precision isn't just manufactured at the factory, It has to be rigorously calibrated on the floor.
Which sounds incredibly complicated.
It is, because fixing it requires tracing this entire chain of mechanical relationships, literally from the tip of the cutting tool all the way down to the physical foundation of the building.
And that is exactly our mission for this deep dive today. We are pulling from a big stack of industrial maintenance protocols, machine tool engineering specs, and mechanical diagnostic manuals to figure out how to trace that chain.
Yeah, a really systematic approach.
We are going to systemically diagnose and fix excessive spindle runout, layer by layer. So we'll start right at the point of failure, the spinning tool itself, and work our way backwards.
The diagnostic approach, it has to be rigorous. When you see a symptom at the tip of the tool, the root cause could be, it could be hidden anywhere in the machine's anatomy.
Right.
Jumping straight to replacing the motor or, tearing apart the internal casing, that's a great way to waste days and thousands of dollars. The protocol always dictates moving from the external interface inward.
So let's start right at that external interface, right where the machine meets the metal. If the tool is shaking, the very first place to look is how that tool is actually being held.
Spot on.
We need to look at the taper fit and the tool holders.
Yeah, because the geometry of that connection is incredibly delicate. The spindle uses this cone-shaped hole, the taper, to grip the tool holder.
Okay.
And the angles of the cone in the spindle and the cone on the tool holder are machined to match perfectly. But if there's wear in that hole or accumulated dirt or even just tiny metallic chips left over from a previous cut,
it messes with the fit.
Exactly. It pushes the tool eccentric.
Eccentric, meaning it's physically forced off its true rotational center line.
It makes me think of having a single grain of sand in your shoe.
Oh, that's a great way to look at it.
Right. To you, that tiny grain feels like a massive boulder throwing off your entire walk. In the spindle taper, a single microscopic metal chip pushing against that steel cone throws off the entire geometry.
It pushes the tool slightly sideways, and suddenly you have severe runout that chatters against the metal and destroys your surface finish.
Yeah, a 0.01 millimeter piece of debris near the base of the taper. It literally acts as a fulcrum.
Wow. Just 1/100 of a millimeter.
It's just that tiny bit. By the time you travel a few inches down to the tip of the cutting tool, that micro deviation has multiplied into a massive visible swing. The tool's tip ends up drawing a circle in the air instead of spinning on a single fixed point.
So how do they even check for that?
Well, to verify if this is the root cause, you use a highly specific diagnostic tool called a test bar, and you pair that with a dial indicator.
And for those who might not have used one, a dial indicator is basically a super-sensitive mechanical measuring needle hooked up to a clock face. You mount the clock part to the machine frame, and you rest the tip of the needle against the spinning cylindrical test bar.
Exactly. And as you slowly rotate the spindle by hand, that needle tracks the physical surface of the bar. If the bar is spinning perfectly true, the needle stays completely still. But if the needle sweeps back and forth across the dial face, it's detecting the high and low points of a wobble.
Which tells you there's a problem.
Right there at the near end of the taper, the engineering specs demand that this radial runout must be kept under 0.0005 millimeters.
Wow.
If it's higher than that, the interface is compromised.
0.005 of a millimeter is virtually nothing. I mean, a human hair is roughly 50 thousandths. So say you measure it and the needle is sweeping wildly. You've got where maybe some scratches inside that cone-shaped hole.
Yeah, it happens.
How do you fix it? Because the engineering manuals suggest something that sounds, honestly, surprisingly low-tech. grinding the inside of this multi-million-dollar machine's taper hole with sandpaper.
I know, right? The idea of taking sandpaper to an aerospace-grade machine tool sounds like heresy.
It really does.
But it is actually a standard practical intervention for minor wear. The technician attaches strips of fine grit sandpaper to an old, perfectly shaped tool shank, inserts it, and carefully laps the inside of the spindle.
So they're not trying to reshape the whole thing.
No, the goal isn't to remove structural metal. It's just to smooth out microabrasions, high spots, or embedded rust that are kicking the tool off center. Now, for deep gouges, sandpaper won't work.
What do they do then?
That requires bringing in specialized technicians who use laser cladding to physically weld new metal into the gouge and then remachine the entire taper back to factory spec.
Okay, so you clean it, you lap it smooth, and the cone is flawless. But the protocols also heavily scrutinize the tool holders themselves, specifically the standard spring collets that grip the actual cutting bit.
Right, because standard spring collets rely on mechanical slots squeezing together to grip the tool. They are inherently prone to leaving microscopic gaps around the circumference of the shank.
Which introduces more wobble.
Exactly. If you are chasing absolute precision and want to eliminate clamping gaps as a variable, the upgrade path involves moving to hydraulic tool holders or shrink fit holders.
Wait, I understand the physical clamping of a spring, but how does a hydraulic holder work in this context?
So a hydraulic holder contains an internal bladder filled with specialized fluid. When you tighten a single actuation screw on the side of the holder, it pressurizes that fluid.
Okay.
The fluid then uniformly compresses an incredibly thin steel sleeve around the tool shank. Because liquids exert pressure perfectly evenly in all directions, the holder grips the tool with 360 degrees of uniform force, perfectly centering it.
Oh, that makes total sense. And what about the shrink fit ones?
Shrink fit holders use a totally different physics principle, thermal expansion. You use an induction heater to superheat the holder, which physically expands the metal hole.
Right, heat expands metal.
You drop the cold tool in, and as the holder cools, the metal shrinks back down, grabbing the tool with thousands of pounds of crushing force.
Both of those methods essentially fuse the tool to the holder, right, making it act like one solid piece of metal.
Basically, yes.
And the data shows moving to these advanced holders can cut runout by up to 50%. There is also a vital rule of thumb mentioned across these manuals. Clean the taper hole before every single tool change, and always default to using short, thick tools whenever physically possible.
Yeah, that mandate for short, thick tools, that comes down to harmonic resonance and stiffness.
How so?
Any tool sticking out of a spindle acts like a tuning fork. When metal hits metal, it generates massive vibration. A long, thin tool lacks stiffness. It will bend and vibrate wildly under cutting forces, amplifying any microscopic runout at the spindle.
Oh. Yeah.
Stiffness scales with the cube of the diameter. So a short, thick tool shank is incredibly rigid. It physically resists bending and forces those cutting vibrations back into machine frame rather than letting them oscillate at the cutting edge.
Okay, so we've diagnosed and perfected the grip. The taper is spotless. We've pressurized a hydraulic holder around a rigid, thick tool. But you spin the machine up, and that dial indicator needle is still sweeping back and forth.
The runout persists.
Exactly.
Well, that tells us the interface is fine, but the shaft itself is shaking. We have to move past the tool and look into the internal mechanics that hold and support that spinning mass.
We're going deeper.
We are diving into the heart of the machine, the internal spindle bearings.
And these are a far cry from the little steel ball bearings you'd find in a skateboard wheel or a bicycle hub.
Oh, absolutely. The forces involved here are staggering. Spindle bearings are subjected to immense axial thrust, which is force pushing straight back into the machine, and radial load, which is the sideways force of the cutter plunging into solid steel.
Right.
Over time and millions of rotations, the highly polished metal balls inside those bearings wear down.
Yeah.
Metal cages spacing the balls can deform.
And that causes problems.
Huge problems. When that wear occurs, the bearing loses its tight physical tolerance. The manuals dictate that if the radial clearance, the physical empty space inside those bearings, exceeds 0.005 millimeters, it translates to catastrophic wobble at the tool.
So how do you even check for worn bearings without tearing the entire casting apart?
The protocol starts with a static tactile inspection. You power the machine completely off, reach in, and literally rotate the heavy spindle shaft by hand. You are feeling for the mechanical feedback.
What should it feel like?
It should feel like heavy, smooth glass. Any sticking, a faint grinding sensation, or even uneven resistance as you complete a rotation indicates internal surface damage on the bearing races.
Let's say it feels mostly smooth, but the dial indicator still shows too much clearance.
Yeah.
This brings us to a highly technical intervention called preload calibration. Now, I have to admit, I struggled with this concept initially. Why would we intentionally apply pressure, which is what preload is, to a bearing assembly that we want to spin as freely and as fast as physically possible? Doesn't squeezing the bearings create unwanted friction?
It seems entirely counterintuitive until you really analyze the dynamic forces of machining. If you have a bearing that spins with zero friction and zero resistance, you inherently have a tiny amount of slack in that assembly.
This reminds me of packing a suitcase.
Okay, how so?
If you pack a hard-shell suitcase loosely, you can snap the lid shut with zero effort. But the moment that bag hits turbulence on a flight, everything inside gets smashed to pieces because the items have enough physical space to gain momentum and slam into the walls.
I love this analogy.
Right. But if you intentionally overstuff it, if you pack it incredibly tight and literally have to sit on the lid to compress it, it takes way more effort to close. You applied preload. But during the flight, nothing shifts.
That is exactly it. The turbulence in this scenario is the violent hammering force of the cutting tool plunging into a block of raw steel.
Right.
If there is even a microscopic gap between the metal balls and the outer rings of the bearing, the spindle shaft will violently chatter back and forth across that gap during a cut. Preload intentionally compresses the entire bearing assembly.
So they squeeze it together.
The technician physically squeezes the inner and outer races together to eliminate all internal clearance. You adjust this axial preload to hit about 2 to 5% of the bearing's rated dynamic load capacity.
And the manuals talk about doing this by installing or removing these razor-thin metal shims behind the bearing flange, changing how tightly the components are sandwiched together.
The technician is literally tuning the stiffness of the spindle. There is actually a fascinating case study in one of the diagnostic logs we reviewed.
Oh yeah, tell me about that.
A machine was exhibiting massive runout, measuring a full 0.03 millimeters. The technicians opened the headstock, remeasured the shim packs, and reapplied an axial preload of 180 newtons. The runout instantly plummeted down to 0.0008 millimeters.
That's wild. To put 180 newtons into perspective for you, that is roughly 40 pounds of continuous squeezing force pushing those bearings together.
Yeah,
Just by tightening the internal suitcase, they stabilize the entire shaft.
exactly.
But what if the tactile test failed? What if you felt that faint grinding when turning it by hand? No amount of shims will fix pitted metal balls.
Right. At that point, bearing replacement is mandatory, and the specifications for these replacements are extreme. You cannot use standard industrial bearings. The manual mandates high-precision P4 or P2 grade bearings.
What does those grays actually mean?
They refer to international tolerance standards. A P2 grade bearing is essentially aerospace-level perfection.
Wow.
The physical imperfections on the metal balls and the raceways are measured in single microns. Furthermore, they use a specific geometry called angular contact bearings.
How are those different?
Unlike a standard bearing where the balls just sit in a groove, the outer ring of an angular contact bearing is thicker on one side, creating a funnel shape. This asymmetric geometry allows the bearing to absorb the massive sideways thrust generated when a tool drives into solid steel without the balls popping out of their tracks.
That's brilliant.
And they must always be replaced in matched pairs.
The installation procedures we read, they read like a surgical manual. They have to be packed with exact volumes of high-temperature grease, and because of that asymmetric funnel shape, the large opening of the bearing must point directly toward the heavy load direction.
The assembly area must be meticulously clean, too. I mean, a single speck of dust inside a P2 bearing spinning at 10,000 RPM will act like a piece of gravel, destroying the raceway in a matter of hours.
Unbelievable. So let's trace our chain. The taper is pristine. The hydraulic holder is locked. The P2 angular contact bearings are freshly greased, installed perfectly, and preloaded to exact specifications.
Sounds perfect.
We turn the machine on, the spindle spins up, but it's still wobbling.
Well, then, the spindle itself is completely sound, but it is receiving corrupted energy. Bearings don't spin themselves.
Right.
They are driven by an external electric motor. We have to move further up the drivetrain and examine the power delivery, specifically the motor couplings.
And the coupling is the mechanical joint that connects the electric motor's drive shaft to the spindle shaft. The diagnostic logs warn that loose drive connections transmit disruptive frequencies straight into the cutting tool.
Yeah, if the bolts clamping that coupling together are loose, the joint acts as a massive vibration generator.
The torque specifications here are non-negotiable. The manuals dictate using a torque wrench to tighten those coupling bolts to precisely 40 to 60 Newton meters,
It has to be exact.
which feels like pulling a standard length wrench
Go.
with about 30 to 40 pounds of force. It's tight, but not like hanging your whole body weight on it tight.
It has to be uniform. But the mechanical bolts are only half the equation. Inside that coupling assembly sits a component that is frequently overlooked during maintenance.
The rubber buffer pad?
Yes, sometimes called an elastomer spider.
This was a genuine point of friction for me when reading through the engineering specs. We are talking about a machine that weighs 10,000 pounds, designed to mill titanium. And the power transmission relies on a squishy, star-shaped piece of rubber.
I know, it sounds crazy.
Shouldn't a machine this powerful use a completely rigid, forged steel connection from the motor to the spindle?
A completely rigid connection would tear the machine apart.
Really?
Electric motors do not produce a perfectly smooth, continuous flow of energy. They operate using alternating current and magnetic fields that switch on and off rapidly. This creates torque ripple, a pulsing, microscopic stutter in the rotation.
Oh, I hadn't thought of that.
Yeah, if you bolt a pulsing electric motor rigidly to a high-precision spindle, those magnetic shock waves transmit straight through the metal, destroying the delicate P2 bearings and leaving visible chatter marks on your machined part.
So the rubber acts as a shock absorber.
Exactly. The rubber buffer pad acts as a harmonic dampener. It absorbs that high-frequency stutter, smoothing the violent pulses from the motor into a fluid, continuous spin for the spindle.
That makes perfect sense. It's filtering the dirty mechanical power into clean rotational energy.
But over years of absorbing those shocks and dealing with ambient heat, that rubber ages. The plasticizers evaporate and the rubber becomes hard and brittle.
And then it stops working.
Once it loses its elasticity, it stops dampening. The torque ripple bypasses the dead rubber, travels down the shaft, and manifests as runout at the tool.
To test for this, the protocol suggests a simple physical rotation test. With the machine off, you grip the motor side of the coupling and twist it back and forth by hand.
Yeah.
If you can feel any dead space if you can rotate the motor even a fraction of a degree before the spindle side catches and starts to turn, you have a gap. That coupling must be rebuilt with a fresh buffer pad.
And once it is rebuilt and tight, the two shafts must be aligned through coaxiality calibration. The exact center of the motor shaft and the exact center of the spindle shaft must form an unbroken, perfectly straight line. Technicians use a laser alignment tool to measure this.
Because it's off even a little bit.
If the motor is sitting even slightly off-center, the coupling will be forced to bend and flex with every single rotation. At 10,000 RPM, that flexing throws wild, chaotic vibrations straight down the line. You physically shim and adjust the motor mounts until the deviation between the two center lines drops below 0.005 millimeters.
Okay, let's take stock of where we are. We've perfected the tool grip. We've tuned the internal bearings and their preload. We've rebuilt the coupling, installed a new dampener, and laser aligned the motor.
The whole system is dialed in.
The entire mechanical chain, from the electrical power source to the cutting tip, is mathematically and physically perfect.
And yet, in some nightmare scenarios, the technician powers up the machine, runs a test cut, and it fails. The tool still wobbles under load.
If the entire internal system is perfect, what else is there? I mean, what's left?
An environment.
Yeah.
If the spindle mechanics are faultless, the laws of physics are actively bending the machine frame. We have to zoom out to the macro level and examine the structural and thermal realities of the installation foundation.
Ah, I see. It's like trying to install a custom-built, perfectly square, incredibly expensive door.
Okay.
You can have the best hinges and those precise measurements, but if you install that perfect door into a house that was built on a shifting, unlevel foundation, the wooden framing of the house is going to sag and twist.
Right.
That perfect door is never going to close, right? Because the space it occupies is warped.
The exact same principle applies to industrial machining centers. People look at an HMC, they see this monolithic block of heavy cast iron, and they assume it is immovable.
It looks immovable.
But cast iron is a crystalline structure. If the concrete foundation it sits on is unlevel, or if the massive anchor bolts bolting it to the factory floor are loose, gravity constantly pulls unevenly on the casting. Over time, the heavy cast iron frame experiences micro-twisting.
Wait, the machine bed itself physically bends?
It bows and twists, and because the spindle housing is bolted to that frame, when the frame twists, it physically alters the original rotational trajectory of the spindle.
Wow.
The spindle is perfect, but it's pointing in the wrong direction. The fix is foundational. The technician must inspect the anchor bolts. They use highly sensitive precision machinist levels tools that can detect a tilt of incredibly tiny fractions of a degree to map out the entire machine bed.
And then they level it.
They adjust leveling jacks under the iron casting until the structural twist is completely dialed out of the frame.
But the environment twisting the machine isn't just about the floor. The engineering specs dedicate a massive amount of attention to something called thermal deformation. The heat generated by the machine actually warps the iron casting.
Yes. When a spindle runs at high RPMs, the internal friction of the bearings and the motor generates substantial heat. That heat flows from the spindle outward into the surrounding cast iron headstock. The front of the casting, nearest the spindle, gets significantly hotter than the back of the casting.
And as we know from basic physics, heat causes metal to expand.
Because the front expands more than the cooler back, the entire massive iron housing physically bows, curving much like a banana.
Just from the heat.
Just from the heat. A 1-meter block of cast iron can grow by several hundredths of a millimeter when heated. That thermal bowing physically tilts the perfectly aligned spindle axis right out of tolerance, causing massive runout at the tooltip.
That's incredible.
It highlights a critical reality in mechanical engineering. Even thousands of pounds of rigid cast iron behave like a fluid, expanding and contracting when subjected to temperature gradients over time.
But you can't stop a machine from generating heat if it's cutting steel at high speeds. So how do you fight the physics of fluid cast iron?
You fight it through predictable consistency. You manage the thermal deformation by forcing the machine into a state of thermal equilibrium before a tool ever touches metal. The mandatory procedure is a run-in period. You turn the spindle on and let it run at operational speed, completely empty, for 30 to 60 minutes.
You just let it spin in the air to warm up, like a car in winter.
Basically, yeah. That warm-up period allows the generated heat to soak completely and evenly through the massive iron casting. Once the temperature stabilizes across the entire structure, the metal stops expanding. The bowing stabilizes into a fixed, predictable shape.
Right, it stops moving.
Only when the machine reaches this thermal equilibrium is the geometry stable enough to perform precision cutting.
And once it is fully warmed up, once the foundation is leveled and the bolts are torqued, you perform the final validation metrics.
The technician puts a dial indicator back on the spindle. After moving through all these layers, the radial runout must finally measure under 0.003 millimeters.
Just 3 microns.
Yeah. Additionally, they use a specialized sensor to check radial vibration velocity,
which measures not just how far the machine is shaking, but how fast and violently the vibration is moving through the housing.
The spec demands that the radial vibration velocity stays under 1.0 millimeters per second, while the spindle ramps through its different RPM ranges. If the runout is under 3 microns, and the vibration velocity is under 1 millimeter per second, the machine is mathematically cleared to cut parts.
This has been an incredibly rigorous journey. We've literally traveled from the microscopic to the massive. We started by wiping a microscopic chip of metal out of a taper hole, clamped down a hydraulic fluid holder, and unpacked the tuning fork harmonics of short, thick tools.
We really covered it all.
We tore into the heart of the machine, squeezing high-precision aerospace bearings with 40 pounds of preload to eliminate the internal chatter. We discovered the vital importance of a squishy rubber buffer pad filtering out the dirty magnetic pulses of a high-torque electric motor.
And the floor itself.
Right. And we ended by wrestling with the literal concrete ground the machine sits on and the thermal expansion of fluid cast iron.
The sheer complexity of an industrial machine is staggering when you trace a single fault line from the tool down to the concrete.
Yeah.
It proves that precision is a systemic achievement, not just a localized fix.
And I think there's a broader, rather profound philosophical takeaway hiding inside all these engineering manuals, something that goes far beyond just diagnosing an industrial machining center. How often in our own lives, in our careers, or in the businesses we manage, do we obsess over treating a tiny, highly visible symptom?
That's a great point.
We stare at the wobbling tool, trying to force it to cut straight, without ever zooming out to realize that our fundamental foundation is completely unlevel. We spend all our energy trying to fix the tip of the spear, completely blind to the fact that the ground beneath us is shifting.
It's all about the foundation.
Sometimes you have to stop staring at the symptom and start checking your anchor bolts. Thank you for joining us on this deep dive. Keep questioning the mechanics of the world around you, tracing the systems from the surface right down to the foundation. And next time you see something wobbling, remember, it might just be the floor.